So we were talking about vaporization and how vaporization is an endothermic process. It requires heat to come in. So, of course, we like to measure things in science, so we can measure that and quantify it. So we call that the heat or enthalpy of vaporization. So we've talked about heats of reaction, the amount of energy that's released or absorbed when a chemical reaction occurs. This is the amount of heat that is absorbed when vaporization occurs. And it's defined as the amount of heat needed to vaporize 1 mole of the liquid at its normal boiling point. It's always going to be a positive number because vaporization is always an endothermic process. It does depend a little bit on the temperature, and that's why this specifies the normal boiling point. So if we look at this table from your book, here's water. Normal boiling point is 100 degrees. So at the boiling point, the heat of vaporization is 40.7 kilojoules per mole. At room temperature, it's 44 kilojoules per mole. So it requires a little more energy, but it's not a huge difference. And then here's information for rubbing alcohol, acetone, and diethyl ether. You do not memorize heats of vaporization. You look them up in a table. So if vaporization is endothermic, then the opposite process, condensation, has to be exothermic, right? Because you can't have energy being created or destroyed just by vaporizing and condensing something over and over again. It'd be great, but it doesn't work that way. So if it took 40.7 kilojoules per mole to vaporize the water, when the water condenses, it releases 40.7 kilojoules for every mole of water. And so this number here, this heat of vaporization, can be used as a conversion factor between kilojoules of energy and moles of water in this case. So let's calculate the amount of heat in kilojoules required to vaporize 2.58 kilograms of water at its boiling point. So this ends up being a unit analysis, dimensional analysis problem. We have 2.58 kilograms of water, and we're asked to calculate how much heat in kilojoules. So over here we want kilojoules. And then we have to figure out how to get from one thing to the other. A piece of information that we have to look up is the heat of vaporization for water. And that's negative 40.7 kilojoules per mole. It was on the previous slide. So trying to get kilograms into kilojoules, kilojoules per mole, if we can get, we're going to go into grams and then to moles. And so that's what we need to do. We'll take the kilograms to grams and then to moles using the molar mass. And then this last step is going to be just the heat of vaporization. So 2.58 kilograms of water. We want kilograms on the bottom and grams on the top. I really can't emphasize enough how important it is to get a firm grasp on metric prefix conversions. These are going to show up over and over again in every science class you take. And I'm seeing students in my second semester in the Chem 1B that are still losing points on exams because they do these backwards. It's really important. What does kilo mean? 10 to the 3. So kilo means 10 to the 3. The kilo, the K is down here. I'm not going to write what it means next to it. I'm going to write what it means on the other side of the line. You follow that pattern, and it will always be correct. There are other ways to do it, and if that works for you, that's great. But this one always works. So we've got our kilograms converted to grams. This will be the molar mass. We want moles on top and grams on the bottom. It's all unit driven. So 1 mole of water weighs 18.02 grams. Then here we're going to put kilojoules on top and moles on the bottom. And then we look at the heat of vaporization, and it's minus 40.7 kilojoules. So minus 40.7 goes in the numerator and 1 in the denominator. So we get a number, minus 5827. How many significant figures? 3. So I'm going to write down 1 extra, and the unit there would be kilojoules. And then when I round that, I'm rounding in the tens place. This is review. I need to be careful. I don't want to round this to 583 because it's 5,000, right? So I can call this minus 5830 kilojoules, or the safe thing is to put it into scientific notation. Now, usually when we do calculations like this, we don't end up with negative numbers. What does that negative mean? It means I did it wrong. We'll blame that on Monday morning. I was remembering this slide. That's condensation. This is vaporization. Right? Good grief. Okay, so this was positive, and this was positive, and these are all positive. It's like I got to the end and thought about it, and I'm like, wait a minute. So, sorry about that. Yes?
So it's positive because you're going from a gas or a liquid to a gas?
Right. It's vaporization. Heat of vaporization is always positive. Energy going in. I had condensation in my brain. Not sure why.
That would be endothermic, right?
Vaporization is endothermic, yes. Condensation is exothermic. Any other questions? It's a great way to start off the morning, trying to confuse your students. Vapor pressure and dynamic equilibrium. So we talked about what's happening with these water molecules. They're moving around. They have an average kinetic energy, meaning some are moving faster than others. And they're moving around in all directions. And so I gave the analogy of this being like playing Red Rover. And little Sally down here, if she is moving in the direction of the surface and is going fast enough, she can break free and get into the gas state. And so even at a low temperature, water will evaporate, right? You know, it rains and it's cold outside, and yet still later in the day the sidewalk's dry. Right? It doesn't have to be warm for it to evaporate. It just evaporates faster when the water's warm. So water begins to evaporate. If this container is sealed, when these particles get into the gas state, they do what gas molecules do, and they go in straight lines until they bump into things. Because they can't escape, they're eventually going to collide with the surface of the water and get trapped again. And so what we have here is we have water molecules leaving and water molecules re-entering the water. Initially, there's no gas particles up here, so there's no condensation. As evaporation proceeds, we get more water molecules in the gas state, and then the rate of condensation increases, and those will keep going until the rates are equal and we have a dynamic equilibrium. We talked about that. So the rate of evaporation and the rate of condensation is the same. Any questions about that? The rate of evaporation depends on the surface area and the temperature. Those are both constant as we watch the progression in this flask. What's not constant is the rate of condensation, which depends on the amount of gas molecules, or the concentration or partial pressure of gas particles. As that increases, the rate of condensation increases. So we see this happening. The rate of evaporation remains constant over time. The rate of condensation in a closed flask increases to a point where it equals the rate of condensation, and then they both remain constant. So we have a dynamic equilibrium. There is a vapor pressure. That vapor pressure depends on the strength of the intermolecular forces. If the red rover line is weak, the rate of evaporation is higher, and the rate of condensation will keep increasing until it matches the rate of evaporation. If the forces of interaction are very strong, red rover line is, maybe the 8th graders at school instead of the kindergartners. You have to run a lot faster to get through, not as many will get through, and so the vapor pressure is lower. So if we have weak forces, you have high vapor pressure. If we disturb a system, we learned about this earlier, Le Chatelier's principle. If you have a system in dynamic equilibrium and you disturb it, it reacts in a way to minimize the disturbance. So here we have a cylinder with a movable piston. It's in dynamic equilibrium. This pentane is evaporating and condensing. If we increase the volume by pulling the piston up, what does that do to the concentration of the gas molecules or the pressure of the gas molecules? It goes down. And so then equilibrium will shift to replace those, to increase the concentration. The other way to think about it is when we increase the volume here, now these molecules have more space to run around in. They're not going to run into the liquid as frequently. The rate of evaporation remains constant, but by increasing this volume, the rate of condensation is going to go down. So the rate of evaporation will just keep going and going and going until it replaces all of that, and we have the same pressure above. Does that make sense? So the rate of condensation is dependent on the pressure, the vapor pressure of that substance. If we decrease the vapor pressure, then we decrease the amount of condensation, and so evaporation will continue until it replaces that. And the opposite is true. If we press down on this, make the volume smaller, now we increase the pressure or the concentration of the gas, and so we cause it to collide with the surface more frequently. Now we have condensation being faster than evaporation, and it will keep decreasing until it matches the rate of condensation. So it doesn't matter what size the flask is. If you give it enough time, you'll always get the same vapor pressure. The vapor pressure does depend on temperature. When you increase the temperature of the liquid, you increase the number of particles that have enough energy to escape into the gas state, and so you'll increase the vapor pressure. And a small change in temperature can give us a big change in vapor pressure. So this is a graph that shows vapor pressure and torr as a function of temperature in degrees Celsius. And so we see that at room temperature down here, about 25 degrees, this red line is for water. The vapor pressure of water is pretty low. But as we increase the temperature, heat the water up, it increases and increases until at 100 degrees, the boiling point, then the vapor pressure is equal to the atmospheric pressure, which is 760. Ethyl alcohol, we see a similar curve, but it hits atmospheric pressure at a lower temperature. Diethyl ether has a boiling point that's just a little above room temperature. And then here we have ethylene glycol. That's the ingredient, a common ingredient in antifreeze. That has a much lower temperature dependence for its vapor pressure. Any questions? It's not a coincidence that the vapor pressure of water is 1 atmosphere at 100 degrees Celsius. The boiling point of a liquid is the temperature at which the vapor pressure is equal to the external pressure. So the vapor pressure of water at 100 degrees Celsius, it has enough energy to make a gas inside of the liquid. And those are the bubbles that you observe when something is boiling. Those bubbles rise to the surface and pop because they're much less dense than the liquid, and so they're not going to stay down there. As they form, they'll come to the surface. So what we refer to as the normal boiling point is the boiling temperature at which the vapor pressure equals 1 atmosphere. So 1 atmosphere is normal. It's 100 degrees Celsius for water. If we change the external pressure, we change the boiling point of the liquid. So this is a heating curve. Here's temperature in degrees Celsius as heat is being added. This would be for water. So you start down here around room temperature, and as you add heat, think of a pot of water on the stove. You turn the burner on, and it begins to put heat into the pot. What happens to the temperature? It goes up, right? The longer you heat it, the more heat you put into it, the higher the temperature goes. Eventually, the water begins to boil. What is not obvious is that once the water starts to boil, the temperature no longer increases. The temperature remains the same. Is what's happening when we have vaporization, regardless of the temperature. It's the more energetic particles that are leaving, right? So the added energy that we're putting into the boiling water cannot go to heating the water because all the hottest particles are leaving and taking the energy with them. And so the temperature of the water remains constant until all of the water has turned into a gas. And then the temperature will rise actually quite sharply. So this has applications in cooking. If you're going to make spaghetti and you want it to, cook very quickly, does it help to boil the water longer before you put the spaghetti in? No. It's going to be the same temperature whether it's been boiling for 30 seconds or for 5 minutes. Boiling it longer won't get it hotter. It stays the same temperature. Any questions? It's kind of a weird thought for a lot of students. The relationship between vapor pressure and temperature is not linear. We go back to this graph and we can see that that relationship is not a straight line, right? It's an exponential relationship, and it can be described this way. The vapor pressure is equal to a constant. I keep forgetting to fix this. Let me fix it right now. That's not what I wanted to do. Good grief. Okay. Push the wrong button. That's not what I wanted to do either. This is an E. So it's a constant times E raised to the power negative delta H over RT. If you take the natural log of both sides of that equation and rearrange it, you get what's known as the Clausius-Clapeyron equation. And that's this one right here. So we can take this exponential equation, and by taking the natural logarithm of it and rearranging it, we can get it into the form of a line where y equals mx plus b. So the slope is equal to the natural log, the intercept is equal to the natural log of beta The slope is equal to negative heat of vaporization divided by R. What we're graphing here for y is the natural log of the vapor pressure, and x is 1 over T. So if we graph the natural log of the vapor pressure versus 1 over the T, we get a straight line, and we can figure out the slope, and the slope is equal to negative heat of vaporization over R. R is the gas constant, so we can get the heat of vaporization by looking at how the vapor pressure changes with temperature. So one way to determine the heat of vaporization is to measure the vapor pressure of the liquid at different temperatures and then graph that data. So here we did that natural log of the vapor pressure versus 1 over the temperature. It's like there's a wall. I don't know what's up with that. So this line is not perfect. This is real data. Real data is not perfect. But you can see that it's a line. And if you looked at the correlation coefficient, you'd find that it's pretty close to 1. There's some random error, but it's distributed around the line. So some points are too high and some are too low. So we can find the slope here. The slope of this line is minus 3478 Kelvin. And from that, we can calculate the heat of vaporization. Here for R, we're going to use the value 8.314 joules per mole Kelvin, because that term will give us the units that we want, and we end up finding that the heat of vaporization is 28.92 times 10 to the third joules, or 28.92 kilojoules per mole. Any questions? So this is a for practice problem in your textbook. It's one that's a little hard to do in lecture because it requires graphing. So I'm just going to talk you through how you would do this. So you're given the temperature in kelvins, and the temperature has to be kelvins because we don't want to have 1 over T be 1 over 0, which is undefined. Here's the vapor pressure in torr. So what we want to graph is the natural log of the vapor pressure. So yeah. Okay. Technical issues. So we're going to take the natural log of each of those values. I'm just going to do one as an example. So the natural log of 0.8. And so that's negative 0.223. And then we're going to take 1 over the temperature in Kelvin. So 1 divided by 200 Kelvin is 0.005. And you would do that for all the data points. This is where Excel or another spreadsheet program is very useful, because you can type this equation in once and copy it down, and it'll do all the math for you, which is a good thing. It's easier, and it reduces errors that you might make punching in all these numbers. You graph the data, you get a slope. The computer will do a linear regression line for you, and it will give you something like y equals minus 14x plus 7. I'm just making up numbers. To find the heat of vaporization, you're going to take this slope. The slope equals negative delta H of vaporization over R. And so you'll plug R in here and multiply by negative 14, change the sign, and that'll give you the heat of vaporization. Any questions? Obviously, on an exam, you would not be required to graph something. So I'd probably give you the graph with the information. We can also express the Clausius-Clapeyron equation in a two-point form, so that instead of needing a whole set of data, you just need information at 2 points. So the natural log of P2 over P1 equals negative delta H over R times the quantity 1 over T1 minus 1 over T2 minus 1 over T1. It can be a little tricky to remember where the 1s and the 2s are. Typically, when we look at delta, the change in anything, it's the second minus the first. It's the final minus the initial. So this is final minus initial, and final on top over the initial. So we can do a problem like this. Propane has a normal boiling point of minus 42 degrees Celsius and a heat of vaporization of 19.04 kilojoules per mole. What's the vapor pressure of propane at 25 degrees Celsius? So we're going to use this equation. This equation has 4 variables, 2 pressures and 2 temperatures. And then there's the heat of vaporization, which is a constant and may or may not be known. So if you know all but one of these things, you can find the others. All but one, find the other. So let's write the equation down before we forget what it is. Natural log of P2 over P1 is equal to negative heat of vaporization over R times 1 over T2 minus 1 over T1. So here we have 2 temperatures, and we're looking for a vapor pressure. You can choose which is number 2 and which is number 1. I like to think ahead and decide which one would be easier to solve for. So we're looking for a pressure. Will it be easier to solve for P2 or P1? P2 is in the numerator, so that's going to be easier. So we're going to call the vapor pressure at 25 degrees P2. That's what we're looking for, and that means that this temperature is T2. Do we want to use Celsius? No, we want Kelvin. So let's convert that to Kelvin. That's 298.15 Kelvin. If that's T2, then this must be T1, right? So T1, convert that to Kelvin. I'm not going to do that one in my head. $273 minus 42, 231.15 Kelvin. They gave us the heat of vaporization. What are we missing? Well, we've got T1 and T2. We're looking for P2. What's P1? 1 atmosphere. So this temperature is the normal boiling point. The normal boiling point is the boiling point at 1 atmosphere. So P1 being 1 atmosphere is hiding in this word. And that's something that'll mess you up on an exam. I'll give you this equation, but I will not remind you that normal boiling point is at 1 atmosphere. Okay, so normally I recommend that you rearrange an equation first and then put the numbers in. When you've got logarithms and compound fractions and things, it gets kind of messy. So we're just going to put the numbers in first and see what happens. So natural log, we're looking for P2, so that stays a variable. P1 is 1 atmosphere. That's going to equal, you've got heat of vaporization is, and we need a minus in front of that, 19.04 kilojoules per mole. We're dividing that by R. R is 8.314 joules per mole Kelvin. And then over here we have 1 over T2, 298.15 Kelvin, minus 1 over T1, 231.15 Kelvin. Always include the units and look at them before you do any calculations. Are the units all good? Well, moles will cancel, right? And the kelvins are going to cancel. But up here I've got kilojoules, and down here I have joules. That's going to be a problem. Kilo means 10 to the third, right? So I'm going to take away the K, kilo, I'm going to write times 10 to the third. That's a fast way of converting things. Just stick the meaning of the prefix in where the prefix was. It's not proper scientific notation. Your calculator doesn't care. So then we do this math, and you need to be careful with your calculator. So what I'm going to do on my TI-36X Pro is negative 19.04 EE3 divided by 8.314 times, and then we'll use the parentheses, 1 divided by 298.15 minus 1 divided by 231.15, close the parentheses, and press equals. And so this is giving me 2.226399. When you're dealing with complicated equations like this, and logarithms especially, you don't want to round this off to like 2 or 2.2. That could give you some error in your answer. Keep a lot of extra digits. Well, what is P2 divided by 1? Just P2, right? So natural log of P2 equals 2.226399. How do we find P? We have to get rid of the natural log. The opposite of natural log is anti-log, e to the x. So P2 is going to equal e to the 2.226399. I've still got that number in my calculator, and so I do e to the x, and then second answer to pull that number back equals 9.26. So pressure equals 9.26. And at this point, I'm not going to hammer you on sig figs and problems like this, but be reasonable, right? The temperatures had 3, the heat of vaporization had 4. It's better to have too many sig figs than not enough. So I'm going to call this 9.266. Now what are the units? Atmospheres. Whatever pressure unit was used on the other pressure is the unit that will be on this pressure, because those units have to cancel out. So this is our answer, 9 atmospheres. Any questions? I can almost guarantee, not on this next exam, but the one after it, that there will be a problem using this equation. And there will be a unit that you have to deal with, like the kilojoules to joules here. So we talked about observing vaporization in a sealed container. We'll build up a vapor pressure, and then things will just be nice and constant. What if we heat it in a sealed container? Is heating sealed containers generally a good idea? No, they tend to explode, or at the very least pop open or burst. So this is done in a very specialized container. If you heat a liquid in a sealed container, what happens is, as the temperature rises, the pressure does as well. The gas, as the pressure increases, the gas becomes more and more dense. The liquid becomes less dense because as you heat liquids, they become less dense. And at a particular point, called the critical point, the gas and the liquid states merge and become one state. It's not a gas and it's not a liquid. It's called a supercritical fluid. So it's hard to get good pictures of this because it has to be in a very strong container, and glass tends to break, right? So here we have a window into this container. We see a liquid and a gas, and as we're heating it, this liquid is beginning to boil. We see the vapor getting more dense, and at some point, at the critical point, the meniscus, the line between the two states, disappears. It's not that it all became a gas, and it's not that it all became a liquid. It's one state is the supercritical fluid. Any questions? That only occurs at a high temperature and high pressure. So it's called the critical temperature. Above that critical temperature, you can't have a liquid. The critical temperature is above the boiling point of the substance. The pressure at that point is called the supercritical pressure. Supercritical fluids are very useful solvents. Supercritical CO2 is used to decaffeinate coffee. So you want to get the caffeine out of the coffee beans without removing all the stuff that makes coffee taste good, or at least taste good to a lot of people. I hate this stuff, but so you got to get the caffeine out without removing other things. And this is a separations problem. How do you separate things? Take out what you want and leave behind the rest of the stuff. So supercritical CO2 will dissolve the caffeine and its fluid, so it'll move away and leave the other things behind. Then when you're done with the coffee beans, they are wet with supercritical CO2, but what happens as soon as you release the pressure there? The CO2 turns into a gas and goes away. CO2 is not toxic. It's in your body. Your body is exhaling it all the time. We breathe it in as well. And so there's no harmful residues left in decaffeinating the coffee. Pretty neat solution.